Good morning, good afternoon, good evening, everyone. It is evening on my side. It is my great pleasure to give this tutorial together with Fergus Imrie, Dr. Fergus Imrie. Fergus, maybe you can say hi as well.
Hi.
And it is our pleasure to give this tutorial at AAAI 2022 on time series in healthcare, challenges and solutions. The reason we decided to give this tutorial and focus the work in the area of healthcare and time series is because on one hand, machine learning drives a revolution in medicine and more generally healthcare and bioscience. And the technologies that you are going to see today, as well as many others that are developed in the area of machine learning, and in particular time series, are very useful for medicine. And we are going to give examples on how these machine learning methods can be used successfully in the medical area to empower clinicians and patients. But equally important, and maybe even more important for us, the machine learning community, is that the medical, healthcare, and bioscience area pose new and important challenges that require new insights and new machine learning methods. So I often say that medicine drives innovations in machine learning and AI. And we hope that today we are going to inspire you, the machine learning community and AI community, to look at some of the challenges that medicine poses. And hopefully we can solve some of these challenges together, again, with the hope of empowering clinicians and patients. What type of transformation do I have in mind? It is my belief that medicine can deliver precision medicine at the patient level, can enable us to understand the basis and trajectories of health and disease, empower healthcare professionals as well as patients, inform and improve clinical pathways, better utilization of resources, while also reducing costs, transform population health and public health policies, and enabling new discoveries, both clinical and new therapeutics. Today, we are going to show you examples from time series and machine learning for time series that will provide illustration across all these different 6 areas. So data-driven machine learning can really provide tools that empower clinicians in a variety of settings, patients by providing recommendations. It can also enable us to develop new hypotheses as well as new discoveries, inclusively new drug discoveries. But also more generally, it can provide analytics and operational tools that can enable administrators of hospitals or clinics to operate more efficiently, healthcare bodies by developing recommendations and clinical practice guidelines that are more effective, and last but not least, provide recommendations for public health analysis and policy, which, as shown in the era of COVID, is extremely important to deal with complex environments such as this COVID pandemic. Most of the tools that you are going to see today are aimed at empowering clinicians. But more generally, what we are describing can be used to empower this entire healthcare ecosystem. Let me be very upfront about the following thing, though. Machine learning cannot do medicine. What it can do, it can provide interpretable, trustworthy, actionable information in the form of personalized risk scores, personalized treatment recommendations, personalized monitoring, and other data-driven hypotheses that can inform clinicians on behalf of the patients they are seeing. And indeed, in our own lab, we are involved in a complex set of discussions with clinicians to understand their needs. So we have developed around 1.5 years a set of online engagement sessions, which we call Revolutionizing Healthcare, where we have 500 plus clinicians from all over the world participating in various discussions which are structured around key themes and key challenges that they need solving by us, the machine learning researchers. So if you are interested to see some of these sessions, which are open only to clinicians, but they are informative for us, the machine learning and artificial intelligence community, I invite you to take a look at our website and our YouTube channel, where you can see some of these conversations that inspired many of the ideas that you are going to see in this tutorial today. One of the important things that we are trying to build is an integrated clinical decision support system for clinicians empowered by machine learning. And you see, for instance, in here, one of our clinical collaborators, Owen McKinney, and you see one of the decision support systems that we have built that is really based on longitudinal information from the electronic health record of a patient. So what we really try to do on the basis of this is provide an integrated patient view and make sure that we capture the time series evolution of the patient as their disease may evolve. And such an integrated patient view is important because the risks of these diseases and symptoms are connected, and the risks and the treatments impact how the patient's health and disease trajectories evolve over time. So what we need is to create this type of ecosystem where care is integrated all the way from prevention to screening, to diagnosis, to treatment, potentially treatment at multiple venues, and which enables all the stakeholders in the care of the patient, whether it's clinicians and nurses, healthcare planners, or the patients themselves. So today's tutorial is going to focus on enabling such a view. And for that, we are going to take into consideration the longitudinal trajectories of patients. So we are going to look at time series models. And of course, there are a variety of methods to model such longitudinal trajectories of patients and issue forecasts on the basis of such longitudinal information. And many machine learning methods have been built over the years to enable just that. Here are just a few examples, ranging from deep learning solutions such as recurrent neural networks and convolutional neural networks or transformers, to more conventional but very powerful machine learning methods such as Gaussian processes. In the tutorial today, we are not going to go into the basics of such time series models. Instead, we are going to assume that a lot of this background knowledge is familiar to you. And if you want to gather additional information, we are highlighting here a few resources that are by no means comprehensive. This is some of our favorites. So for instance, you see two excellent tutorials on forecasting time series and understanding LSTM networks, but also more conventional works from Gaussian processes that, as I mentioned, are still very powerful, inclusively a very recent tutorial on the art of Gaussian processes, all the way to state-of-the-art techniques that include neural ODEs and beyond. So we are going to refer you to these excellent resources as well as many others that you can find on the web and in past tutorials at main machine learning conferences for the background information. Instead, what we are going to do today, we are going to look at what time series in healthcare, what challenges this particular application of time series data in healthcare poses. And this is actually a very multifaceted problem. It involves using longitudinal data to issue time series forecasting. It involves time to event analysis over time, survival analysis. It involves looking at the effect of different treatments and interventions over time through treatment effects. It enables early diagnosis of disease, but also personalized screening and monitoring over time, where we need to determine what information is to be acquired and at what moment in time for a patient. And last but not least, understanding how we can cluster over time patients with the overall goal of better understanding of how disease heterogeneity, as well as evolution of disease over time. So these are some of the multiple aspects that play a role when we think about time series data in healthcare. We are going to highlight in these tutorials the unique characteristics and challenges of these different problems and provide solutions. So the first part of the tutorial will be tailored, will be focused on tailoring the development of time series models to specific healthcare challenges. And in the second part of the tutorial, we are going to describe how we can make such time series models as useful as possible for clinicians and patients. If you are interested to read more about some of the materials we present here, a subset of these materials are described in detail on our website in a research pillar that we call time series. And if you are interested to engage in more discussions with us about this particular topic, especially its applications to healthcare, we invite you to join an engagement session that we also started around 1 year and a half ago that we called the Inspiration Exchange. And the focus of this is to have discussions with interested machine learners and artificial intelligence researchers interested in healthcare, trying really to understand this particular area and develop together methods for revolutionizing healthcare. So if you are interested to continue the discussion with Fergus and me beyond this session today, we invite you to subscribe to this particular engagement session on our website. But without further ado, let me start with our tutorial. So first, I would like to talk about dynamic forecasting, how we can use longitudinal time series data to issue predictions and forecasts over time. An important challenge associated with this in healthcare is the unique characteristics of the healthcare data, where we have multiple streams of measurements that may come from various domains. They may be tabular data, it may be imaging data, it may be very diverse data that is measured over time irregularly, and which is also informatively sampled. So the fact that we have data at a particular moment in time or not matters. Data is not collected at random. And we are going to describe this particular information acquisition process more a little later. But we need to learn on the basis of this information. And we may be interested to forecast different outcomes of interest. For instance, different diseases, the onset of different diseases, but also the evolution of different diseases over time. And an important challenge here is that the time at which a particular disease, for instance, cancer, has occurred in a patient is unknown. We only know the time at which the disease was diagnosed, but not the time when the disease started. Also, what makes this problem challenging of issuing predictions on the basis of such complex data over time is that different patients are different, depending, for instance, on the genetic characteristics of the patients, of other such factors. We can have many possible patterns. So we need to learn to issue forecasts over time on the basis of such complexities. So what do we really try to achieve here? We want to build disease progression models with the overall focus of both understanding as well as forecasting. So a first step is to use time series data, whether it is electronic health record data, data from disease registries, or other such longitudinal data, to build disease progression models. And for that, we need to carefully craft models that are actionable for clinicians. Then we need to learn on the basis of the available data at training time, the model parameters. At runtime, for the particular patient and their information we have so far, we use such trained models to issue forecasts about events of interest for this particular patient. For instance, on the basis of the longitudinal information we have about them, what is the probability that within a certain amount of time the patient is going to experience a particular event of interest, such as, for instance, a heart failure or a cardiac event. Also, we want to understand how disease progresses more generally, with the overall goal of understanding and also enabling early diagnosis. We want to do that at the population level, at the subgroup level, but also personalized to the patient and their unique characteristic. Current disease progression models, as you find in state-of-the-art clinical papers, often use Markov models. So they model disease progression passing through a set of disease stages that are observable. And also often such disease progression models are used to model one disease at a time. For instance, you can see prostate cancer being modeled in this particular way, as well as many other diseases. A disadvantage of such modeling is that besides the fact that it assumes that we can observe every stage of the disease, which is often not the case, it also has the disadvantage that it's modeling the average patient. So this is not personalized to the unique characteristics of the patient. One particular advance on top of this is to model the progression of disease using a hidden Markov model. And this is already a big advance because we no longer then need to assume that all the different states that the patient is passing through in the progression of their disease is observable, but rather on the basis of the observations we make, for instance, clinical measurements, lab measurements, and other, let's say, diagnoses or observations, we can infer the hidden disease stages of the patient. So this enables us to model more effectively the observable data. But this is still not enough because in medicine, the history of the patient matters. For instance, the way in which a particular disease has evolved, how long the patient has been in a particular state, for what is the order of the different states through which the patient has passed through. All of that matters. And Markov models, hidden Markov models, are not enabling us to measure that. Also, another disadvantage of these models is, again, that they assume that we are dealing with a population level progression model that is not particularized to the patient in front of the clinician. It doesn't enable us to create individualized clinical trajectories. So can deep learning, can recurrent neural networks and other types of deep learning methods provide a solution to this? Well, first we need to understand what is the goal of these disease progression models. A first goal is to accurately forecast individual level disease trajectories. And for that, many of the current advances in deep learning are going to be sufficient. But we also need to fulfill a second goal, understanding disease progression. And the reason this is important is we need to understand the underlying latent structure of disease evolution to be able to do early diagnosis or enable us to understand patient subgroups and define better phenotypes, understand the progression of different classes of patients and their evolution over time. So if it is for us to consider, for instance, recurrent neural networks as a solution to the time series forecasting problem in medicine, a disadvantage of such models is that they are uninterpretable, lead to uninterpretable predictions, as well as uninterpretable latent structures. A big advance in this agenda happened a few years back through the methodology called RETAIN, and RETAIN stands for Reverse Time Attention Model. And this is a very powerful machine learning method which achieves high accuracy while remaining clinically interpretable. And as you can see in here, it is based on the two-level neural attention model that detects influential past visits and significant clinical variables within those visits, for instance, diagnosis. And a powerful ability of RETAIN is that it mimics the physician practicing by looking at the electronic health record data and in reverse time order, such that the clinical visits are likely to receive higher attention and further away clinical visits less attention. So this is how RETAIN operates. So at this stage, we can say, is this enough? Is RETAIN sufficient to address the various problems we need to solve in dynamic forecasting? Well, while the first goal is very well solved by RETAIN, the second it is not. And the reason is RETAIN provides interpretable predictions, but it doesn't have an interpretable latent structure. It has an uninterpretable latent structure provided by the recurrent neural network. And this is interpretability in the latent structure is important because, as I mentioned upfront, currently in medicine, people are often modeling disease progression through a set of stages or states that are interpretable. So having interpretability in the latent space such that a clinician can understand the current state of the patient and the evolution over time is essential. So a solution to this problem is this attentive state space model, which we have introduced a few years back, which combines the powerful ability of Markov models and hidden Markov models to model the probabilistic structure of the states and state transitions with the ability of deep learning models such as recurrent neural networks to model state dynamics. So you see here this combination in the attentive state space model, which is a general and versatile deprobabilistic model that is non-stationary in nature. So in this way, we are setting attention, but not like in RETAIN to the observation, but the attention is set on the state. So what you see in here is this attentive state space model where the attention weights are determining the influences of past state realizations on future state transitions. So now we have the advantage that we don't only have interpretability at the level of observations, but also interpretability at the level of states. And here, for instance, heavier lines represent bigger attention weights. So here is how much the fact that the patient has been in a particular past state in the past influences the transitions and the trajectories into the future. Also, because now we are having recurrent neural networks rather than hidden Markov models, we are having a non-stationary trajectory that we can model going beyond Markov models. And these attentive state space models are repeatedly updating the attention weights to focus on the past state. So this overcomes the shortcomings of the current Markov models. And you can see here that the attention weights are creating actually a soft version of a non-stationary variable ordered Markov model. And these underlying dynamics of the patients are changed over time based on the individual clinical context, such as, for instance, genetic information or other environmental information. And the memory is now shaped by the patient's current context. And this could include not only clinical events or diagnoses, morbidities and comorbidities, but also interventions such as treatments. In this way, we have an entire ecosystem of clinical models. So this attentive state space model can be viewed as a superset of a variety of other powerful models, whether it is continuous time or discrete time, hidden Markov models, deep Markov models, variable order hidden Markov models, or multitask recurrent neural networks. How powerful or how complex the clinical model needs to be should be learned from data. So given a particular data set from a particular disease, we ideally would like to learn how complex the model is on the basis of the available data. Let me now go one step further. We discussed predictions, but we want to go beyond that. We would like not only to say, given the observations that we have so far, what is the probability that the patient is going to experience this particular event of interest, for instance, cardiovascular event, 3 years in the future. We want, in addition, to understand how the probabilities of these different events vary over time. In other words, we want to do time to event analysis or survival analysis. Usually this is done on the basis of static data, but here we would like to do it on the basis of time series, dynamic data. So we want to do dynamic survival analysis. So what type of data we have at our availability? We have data sets like the one I'm highlighting here, which comprise histories of longitudinal measurements with different numbers of measurements being taken at irregular time intervals, where each patient experiences a number of events of interest and has its endpoint potentially censored. And note here that tau is either the time at which an event of interest, for instance, a cardiovascular event occurred, or the time at which the subject was censored. And by censoring here, we mean the patient disappeared from follow-up. We do not know what has happened to the patient. Maybe the patient has moved to another clinic or hospital. In either case, the subject was known to experience no event at time prior to tau. Then the goal we are trying to achieve here is to estimate a dynamic cumulative incident functions as shown in here. So this CIF, this cumulative incidence function, is here shown the probability that the patient didn't experience up to time tau the event of interest K. And this is based on the longitudinal measurements accrued by the time at which we want to issue the risk predictions. And also the patient was still alive at the time of the last measurement. So we know that it has not died. So on the basis of such information, we are projecting into the future and we are estimating this time, the time to event, the probability of the patient experiencing the event of interest K over time. So the estimation of such incidence of the occurrence of an event can happen while considering not only one particular event of interest, K, but rather multiple competing events over time. So in the future, somebody may potentially experience a variety of cardiovascular events or cancer and cardiovascular events. So this type of formalism enables us to model over time these different competing risks. You see here a schematic of a particular method that we have developed that we call dynamic deep hit, but other solutions exist. Here, the idea is that we use a machine learning method to really do this time to event analysis for the different events of interest. And we train a machine learning model at training time. And then at test time, for the new patient in front of the clinician, we are issuing predictions of risk of the various events of interest. And also, not only predictions, but we can also understand why certain variables have been important. For instance, we can look at covariate influence and temporal importance of these covariates over time with respect to the various predicted risks. So what is the architecture of this particular method that I'm describing here is a recurrent neural network with temporal attention similar to retain, but different in the following sense. We not only have one event of interest, but rather multiple events of interest, K events of interest, So we have a multitask network where we have for every event a cause-specific subnetwork being trained. What is interesting in this particular case is the architecture that we have used with respect to especially the loss functions employed. So not only we have a multitask architecture, but also we have 3 different losses that play a role in training this particular dynamic deep hit network. So we minimize a total loss function that is specifically designed to handle these longitudinal measurements, as well as the right censoring, the fact that the patient may be lost to follow-up. And this is the sum of these 3 terms shown here, where L1 is the negative log likelihood of the joint distribution of the first hitting time and the events, which is necessary to capture this first hitting time in the right sensor data. Then the second loss combines the cause-specific ranking loss function to concentrate on discriminating, estimating individual risk for each cause. And the third loss incorporates the prediction error on trajectories of time-varying covariates to capture this hidden representation of the longitudinal history and to regularize the network. Now, the first loss function is the negative log likelihood of the joint distribution of the first hitting time and the corresponding event, considering the right censoring, which is extended to the survival setting where the history of the longitudinal measurements and the K competing risks are available. And really more specifically for a patient who is not censored yet, it captures both the event that occurs and the time at which the event occurs, as shown in here. And for a patient who is censored, it captures the time at which the patient is censored, lost to follow-up. And in both cases, we condition on the longitudinal measurement recorded until the last observation. The second loss function incorporates this estimated CIF function that I described previously, and this is calculated at different times, the time at which an event actually occurs, in order to fine-tune the network to each cause-specific estimated CIF. And to do so, we utilize a ranking loss, which I'm not showing here because it's quite complicated, but which adapts the idea of concordance. The fact that a subject who dies at a time tau should have a higher risk at time tau than a subject that survived longer than tau. And this is really more complex a definition in the longitudinal setting than there is in the static use of survival analysis. Finally, the last step is this step ahead prediction loss. And longitudinal measurements on time-varying covariates, such as the trajectory, for instance, of biomarkers and the presence of comorbidities over time, may be highly associated with the occurrence of the clinical events. And thus, we use this third loss to introduce really an auxiliary task in the shared subnetwork, which makes predictions, YI, on the basis of the step-ahead covariates of our interest, to regularize really the shared subnetwork such that the hidden representation preserves the information for the step-ahead predictions. And what you see here is a pictogram of how dynamic deep hit uses information over time. You see that every time the patient is seen by the clinician, we have the model being reset, and we learn over time and we issue predictions of the patient having different types of events of interest. The best way to really understand how this dynamic survival model operates over time, as well as how clinicians use this in practice, is by taking a look at our Revolutionizing Healthcare session of October 2021, where our collaborator, clinical collaborator, Vincent, is discussing the use of such time-to-event analysis over time in the context of prostate cancer. Fergus, I think that now is the time for you.
Thanks, Mihaela. Okay, so far we've discussed prediction models and we've discussed survival analysis. I now want to turn our attention to the quite different topic of clustering and phenotyping of patients. These concepts are particularly important in the time series setting for the following reasons. So disease progression manifests through a broad spectrum of longitudinal patterns, and understanding these underlying progression patterns can be extremely challenging for both clinicians and patients alike. One valuable approach that's commonly used within medicine is called phenotyping, which is essentially just grouping together similar patients. However, the immediate question we have is how should we group these patients together into subgroups? Here is an example of 3 patients with breast cancer, and the figures illustrate representative longitudinal observations, which are BMI, mammographic density, and cancer antigen values. Based on a conventional notion of clustering, it's very likely that patient A will be grouped together with patient B because the longitudinal observations of these 2 patients appear very similar compared to patients A and C, for example. I do want to note now, though, that the time series settings already introduced an additional complexity compared to just the static setting. And that is, how do we actually measure the similarity between 2 time series in the first place? 2 popular approaches are dynamic time warping or autoencoder-based methods. For example, autoencoder methods find a latent representation in which a distance can be computed, which then allows patients to be clustered and provides your similarity metric there. Is this notion of clustering the right one? We don't believe so, based on our discussions with clinicians, and we think much more is needed in medicine. What clinicians and patients actually want to understand is what types of events or clinical outcomes are going to happen in the future. And for this, we need a new notion of clustering that extends beyond clustering based on past observations. For example, what if we know that patients A and C actually both died from breast cancer? And we could predict this perhaps based on increases in both their cancer antigen values and their mammographic density over time. Should we still really put them into different clusters? Or in fact, should they be the same cluster? In our new notion of clustering, we believe that patients A and C should be grouped together since we anticipate that they will have similar future clinical outcomes. And the key idea here for doctors is that by clustering in this way, the identified clusters provide prognostic value for anticipating future outcomes. So this new notion of temporal phenotyping was introduced in a paper published at ICML 2020. And as mentioned, in this notion of clustering, the phenotypes are designed to be predictive of similar future outcomes. And the use of these predictive phenotypes, rather than ones based on the observational similarity, allows doctors and patients to actively plan for potential future outcomes. The focus now is, how do we learn such discrete representations of past time series data that can best describe the future events and outcomes of interest? So we can formalize this problem of learning discrete representations as the problem of identifying predictive clusters, hence the link between phenotyping and clustering. The idea here is that we can first learn continuous representations in a latent space for each input sequence, and then we can find an associated discrete embedding for this continuous latent representation. And this can be achieved by finding cluster assignments and cluster centroids of the input sequence in the latent space. So to formalize this, let's just introduce very briefly some notation. And so that at each time t, we have an input sequence xt, which is a longitudinal observation for a given patient. And we have an output label yt, where the outputs are the clinical outcomes of interest, such as comorbidities or death or other adverse clinical effects. We define st as the cluster assignment to the given input sequence at time t, and define the set E as a set of cluster centroids in the latent space. To achieve our goal, the objective is to minimize the KL divergence between the label distribution given the input sequence and that of the cluster assignment. This is equivalent to the objective shown on the screen, which is that of minimizing the difference in the label distribution given the continuous latent representation and the label distribution given the discrete representation or cluster assignment. However, solving this objective given in equation 1 is highly non-trivial. First, this is an NP-hard combinatorial problem, and in particular, we need to both estimate the KL divergence and find optimal cluster assignments and centroids. Second, assigning a cluster to the input sequence involves a sampling process which is non-differentiable. To address the first of these challenges, we can divide solving equation 1 into iteratively solving 2 subproblems. And for the second of these challenges, we can allow backpropagation in the sampling process via a reinforcement learning approach and training in an actor-critic framework. Putting this all together, I'm going to describe a recent approach from our lab called ACTPC. This model consists of 3 components: an encoder, a selector, and a predictor, together with a set of embeddings, each of which represents a cluster centroid. The encoder maps input sequences into the latent space. The selector network then provides a discrete cluster assignment for this input sequence, which can be mapped to one of our embeddings. Finally, the predictor estimates the label distribution given either the continuous encoding or the discrete embedding. So how do we train such a model? In particular, we have 2 subproblems to solve and the challenge of discrete cluster assignment. So let us first consider how to optimize the various network parameters of the model while fixing the cluster embeddings. So we train this first by saying that the clusters should be predictive of the label, and hence we use a predictive clustering loss, which closely resembles a standard supervised loss. However, this loss alone isn't enough. And recall I mentioned that this is an NP-hard combinatorial problem. A critical question is how to avoid trivial solutions, such as the selector simply assigning equal probability to all of the embeddings, or the embeddings collapsing into a single point. In both cases, there's no distinction across clusters, and the network has failed to learn any meaning, clustering, or phenotyping. Hence, when we're training the network parameters, we also train to minimize the sample-wise entropy of cluster assignment. Minimizing this loss forces the selector network to select one dominant cluster for each sequence. So now that we know how we're going to train the network components, how do we optimize the embeddings? This is achieved with the same predictive clustering loss we used to solve the first subproblem, together with an embedding separation loss. And this embedding separation loss forces the label distributions of different embeddings to be different, preventing the model from degenerating to a trivial solution. Finally, I'll illustrate how such a model might work in practice with some runtime examples with 2 representative patients who have cystic fibrosis. This is a particularly interesting disease to study due to its heterogeneous nature of how it evolves. So if we consider patient A on the left, patient A was first assigned to cluster 1 because this patient had a low risk of developing any comorbidities over the next year. At time step 2, based on updated observations, the patient was reassigned to cluster 9 due to the high probability of developing asthma in the next year. Similarly, this patient was then reassigned at time step 5 to cluster 3 due to an increased probability of developing liver disease in the next year. And you can see a similar trajectory for patient B. And what's crucial here is that this clustering allows clinicians to really plan for these future outcomes and perhaps alter the treatment of patients. I think with this, Mihaela, I think I'm going to pass back over to you to cover screening and monitoring.
Okay, so what we are going to describe next is the problem of screening and monitoring. So we made predictions over time and we cluster the patients as they progress over time. But what about monitoring patients that may have been diagnosed with a particular disease? How often should we monitor them? Or if the person didn't develop the disease yet, when should we screen the particular patient? So the type of questions you would like to answer are, who shall we screen? When shall we screen this patient? With what particular modality or what type of observations should we make? And this is true both for patients that have already a disease and they need monitoring over time, or for patients that did not yet develop a particular disease, but need to be screened due to their particular high risk? In order to answer this question, we need to actually pose and as well as answer and formalize a complex question. What is the value of various information over time for the event of interest, for instance, a particular morbidity, for instance, cancer, that we would like to predict, or in the case of a patient with cancer, a particular reoccurrence of cancer, and how this value of information for this particular event will be different for this particular individual, this particular patient, as opposed to other patients. So what we would like to ask is a question as shown in here. We have different types of observations so far. So we are at the second time step. And we would like to ask, when should the patient come next if what we are wanting to detect is the event of interest, for instance, cardiovascular disease. And at time step T, we have an array of measurements so far, and we must decide at the next time, what is the next time at which the patient should come to take new measurements, and what type of measurements, if we can take multiple measurements, what type of measurements to conduct at that particular moment in time. This is the problem of personalized monitoring. And we measure the information provided by the new samples by the effect on the event of interest, the prediction of the event of interest. So we define the predictive loss from not monitoring and sampling as the increase in uncertainty of our prediction of the event of interest, and the predictive gain as the decrease in uncertainty associated with the prediction of interest. And our approach is really to find the first actual time, let's say a time tau, at which the estimated predictive gain provided by new sample exceeds the cost of sampling, keeping in mind that the cost of sampling may be different for different measurements, and to make the set of measurements at the time tau that maximizes the estimated predictive gain minus the cost. And our objective will be to find a set of measurements that maximizes this net reward, which we consider to be this information gain minus cost. So what we are trying to do here is to look at this trade-off between, on one hand, monitoring and screening, which is costly, and the value of such information acquisition from monitoring and screening versus the cost associated with this. So in other words, rather than telling a patient you should come in 3 months or 6 months in a predetermined set of predetermined time horizons, we want really to make sensing and monitoring an active choice. And we want to make it personalized to the patient and the performance associated with acquiring this information. The challenge, though, in solving this problem is that the value of information is unknown and dynamically changing. So it needs to be learned on the basis of data. So this is a very different type of problem than the ones we described so far. And this is a unique characteristic of medicine. This type of problem occurs naturally in medicine. So how to do this? One particular way in which we can think about that is to trade off the performance against the cost by learning through a neural network at training time how to issue predictions at various cost performance points. So for that, we are going to create and learn multiple representations, showing here at the bottom. So we have R different types of representations at various performance levels associated with different measurement costs. So each representation is learned on the basis of a particular set of available data given, and the predictions are made given the available data by imputing the missing data. And these sets are constructed recursively and adaptively. So what you see here is how we start with a particular data set. If this data set has missing information, we can impute that information. Then we can predict on the basis of a particular dynamic forecasting method. It can be an RNN or it can be one of the methods that we described so far. We can estimate the error associated with a particular prediction. And then we can create a new representation by throwing away in an adaptive sampling way more information and create another representation at an even lower cost. One way in which we can do imputation will be described later. It's called multidimensional RNN, but any method for dealing with missing data can be used. Then at runtime, we are going to use these different types of representations to determine when to acquire information next. And an important aspect of the solution to the active sensing problem is that there are differences between the operation at training time and at runtime. At training time, we can use data at the current time to infer the missing data at an earlier time, so we can operate non-causally, but we cannot do so at runtime. So at runtime, we are going to project into the future, and on the basis of that information, we are going to determine when to sense next, when the value of additional information will be high enough to warrant this new sensing. However, after a particular visit has been done and information has been gathered, we can go back in time and we can do imputation in a causal way. Now that we discussed screening and monitoring, what about using this information to detect disease early, to do early diagnosis? Well, this is a very complex problem. And just to understand how complex a problem this is in medicine, I'm highlighting it here with two exemplars from the British Medical Journal, BMJ, which shows how complex the decision process is for early diagnosis in cancer. And the current thinking in early detection and diagnosis is based on static risk prediction, where patients are segmented based on population-based risk, which are usually based on only few variables and only very rarely are using time series longitudinal data. And usually this risk of having a particular disease of interest is calculated only once during the lifetime of a patient. And on the basis of this, risk scores are then used to, and they lead to guideline-driven management of patients, which is often rigid. And what's even worse is that many diseases even lack such guidelines and protocols. So early diagnosis is often not done, and often diseases are diagnosed in patients late. So in order to be able to overcome that, machine learning can help clinicians by providing a quantitative understanding of disease progression over time. So how can we detect disease early? Well, as we discussed before, we have observations over time. This may be static information such as the family history of a patient or genetic information of the patient, as well as longitudinal information, for instance, early signs and indicators. Then as the disease progresses, non-specific symptoms followed by specific symptoms. But the underlying progression of disease is not observed, is hidden, and needs to be learned from data. So we need to learn on the basis of the data that we have what underlying hidden state the patient is in. Is the patient still healthy? Or did the patient is emerging into a situation in which pathology starts to be present? We need such disease progression models. Fortunately, we have methods like the ones we described before, for instance, hidden Markov models or the more advanced attentive state space models. In that case, on the basis of the observations we have so far, we can infer the current state the patient is in, and on the basis of this, issue predictions of the future. So what is useful is to learn on the basis of the available data, the hidden Markov models, or the attentive state space model that allow us to model these transitions over time across the underlying hidden states of the patient. And then at runtime, we know that the patient has had, for instance, a set of observations up to time 3, and then we can predict when pathology will be present. For instance, pathology may be present at time 5, and hence, on the basis of this, we can prompt the clinician that this may happen, and thus they need to ask the patient to come early at time 5, and a particular screening can be done to detect disease early. In this way, we don't need to wait all the way to time 7 when a particular symptom has already occurred and the patient has symptoms, but rather identify disease early before such symptoms have set in. So we can use such longitudinal trajectories of disease, especially ones that have interpretable disease states, to do early diagnosis. If you are interested in understanding what type of requirements we have in terms of machine learning models for early diagnosis, we have a set of 2 engagement sessions with clinicians. One is already posted online, has taken place on February 8th of this year, and the next one will be on March 10th. Again, take a look at our website to see this conversation with clinicians. So far, we have discussed how to really make predictions. What about interventions? Fergus is going to talk about how to deal with treatments over time.
Thanks, Mihaela. So yeah, as Mihaela mentioned, we're now going to discuss how to deal with treatments over time. And this is going to be the final challenge we're going to discuss in this part of the tutorial. And this is a really key aspect of medicine, since understanding the effect of different interventions is critical to assist doctors to know how to actually treat patients. So in this scenario, we have patients that have been diagnosed already with a particular disease, such as breast cancer, for example, and we have an entire history for that patient over time. On the basis of electronic health record data, what we want to understand is what is the best future treatment plan for a given patient, and to determine causal inference models that allow us to answer these type of questions. These causal inference models can then be used to estimate for every individual patient what is the best treatment course over time. In particular, we wish to answer what-if questions, such as how to treat or with what treatment, when to give treatment, and when to stop treatment. And we can answer these questions by computing counterfactual outcomes for the patient over time. I really want to emphasize that this is not a simple prediction problem, such as simple forecasting or prediction that we discussed earlier. There's rather a much more complex causal effect inference problem, where we need to learn to perform causal effect inference on the basis of longitudinal observational data. In particular, we must do this using only the factual outcomes that are available in the data, i.e. we don't observe the counterfactuals, we only observe the factual outcome given the treatment plan that the patient actually received and the history of a given patient. This is very challenging in the time series setting. So in the past few years, there's been a lot of work in the machine learning and artificial intelligence literature about causal effect inference in the static setting. However, in the time series setting, this is a lot more challenging because of the need to deal with time-dependent confounders, which bias the treatment assignment in the observational dataset. So what is a time-dependent confounder? These are patient covariates that are affected by past treatments, which then in turn influence future treatment decisions and indeed outcomes. It is necessary to develop methods that deal with these time-dependent confounders in order to derive accurate models for counterfactual estimation. An example of early work for handling time-dependent confounding bias is marginal structural models proposed about 20 years ago. And these have been a key method in statistics for dealing with time-dependent confounding bias. A key component typically employed in such models is inverse probability weighting, which attempts to correct for the time-dependent confounding bias via a reweighting approach of the observational data. More recent work has combined the ideas of these marginal structural models with more modern, powerful deep learning models, such as recurrent neural networks, to create recurrent marginal structural networks for estimating treatment effects over time. However, both marginal structural models and recurrent marginal structural networks suffer from numerical instability and high variance. Hence, more recently, our lab has proposed an alternate way of handling time-dependent confounding bias for estimating treatment effects. And this is achieved with a new type of representation learning that enables us to balance the representations and achieve treatment invariant representations to handle the confounding bias. Going into a bit more detail, counterfactual recurrent networks are a sequence-to-sequence architecture for estimating counterfactual trajectories. The past information or patient history, together with any interventions that have already been made, is used as input and encoded by a recurrent neural network. This encoding can then be translated or decoded into a sequence, allowing us to ask the type of what-if questions necessary to determine optimal treatment for patients. The encoder learns representations using the factual observational data we have available by predicting the observed outcome given the treatment that was administered. However, if we solely learn representations based on this factual data, we'll end up with a poor model due to the time-dependent confounding bias. To handle this additional challenge, the encoder is trained such that the representations are treatment invariant. And what this really means is that it's not possible to predict the factual treatment that was administered to the patient using the representation alone. And this is achieved in this work by a novel way of using domain adversarial training together with gradient reversal layers, improving on the work of Gan and et al. So I think this concludes the first part of the tutorial, which is the challenge of time series models. And I'll now pass back over to Mihaela to introduce part 2 of the tutorial, which is about making time series models as useful as possible.
Thank you, Fergus. So, as Fergus has said, we have discussed so far a variety of topics about prediction, early diagnosis, monitoring, and treatments. But how to enable all of this and how to make this more interpretable, more trustworthy, and more robust? A first issue we need to deal with is the fact that we have many different types of time series models. At the beginning of this talk, I described recurrent neural networks. I discussed various methods that may employ attention, different types of attention mechanisms, and also different types of architectures. And the question is, which is the best time series model if our focus is on performance? We have different types of time series data sets that may exhibit different types of temporal distribution shifts, and the risk factors may be changing over time. So a natural question to ask for somebody who wants to use these machine learning models to do dynamic forecasting for a particular time series data set is, what model should be used? And potentially, if one wants to employ a variety of models, how can we select the best model to issue the dynamic forecasting at every moment in time? We cannot possibly do this in a manual fashion. We need to have a systematic way to select models and select which models should be used over time as the time series data is evolving. So for that, what we need to do is model selection, but unlike model selection for static data, where we just need to select the best model for the cross-sectional data, here, because the data is evolving over time, different models may be best at different models at different moments in time. So we need to do stepwise model selection. So what I'm going to describe now is a method for doing stepwise model selection for dynamic forecasting via deep kernel learning. But before I'm going to go into that, I want to highlight to you why this problem is challenging. So we need, usually when we do model selection, we need to do some type of Bayesian optimization. And the objective will be to select the model with the best performance at every moment in time. And usually, multiple objective Bayesian optimization deals with optimizing multiple objectives in a trade-off relationship. And if for whatever reason we were constrained to select a single prediction model for all time steps, then the stepwise model selection problem would reduce to this type of multi-objective Bayesian optimization. But the challenge associated with this is that if we would model this problem in this way, the complexity associated with this is very high. So the question is, can we really do better? Yeah. So what is the challenge associated with this is that this multiple objective Bayesian optimization deals with this multiple objectives simultaneously. So one particular solution to that may come to our mind is to do multitask Bayesian optimization, which deals with transferring knowledge gained from previous optimization tasks to new tasks, in this case from the previous time series predictions to the current time series prediction. In this way, subsequent optimizations are more efficient. And this setting applies in this case to the problem where successive batches of data are available or accumulated over time, such that prior training models may require retraining. So this will provide us with the ability to do warm start. But the disadvantage of this is that this particular multitask Bayesian optimization method requires evaluating deep learning models on large data sets, which is expensive. And we are also faced with the problem of solving T up to time T separate Bayesian optimization procedures in a sequence. And it's unclear how up to the current moment in time we need to allocate the evaluations across these different subproblems. Also, this does not take full advantage of the information available across the different time steps, across the different acquisition functions. So in contrast to such multitask Bayesian optimization, our goal is to take full advantage of the potential correlations among the black box functions, as well as information from the acquisition functions by learning the models for all time steps jointly. So for that, we developed this method called, highlighted in here, which we call it SMSDKL, which is stepwise model selection based on deep kernel learning. And this is a novel Bayesian optimization algorithm that uses deep kernel learning to solve the multiple black box optimization problem jointly and efficiently. And in contrast to the previous setting, we now can solve these multiple black box optimizations in an effective way using deep kernel learning. So this is why we call this model SMSDKL. How does this look like? How can we really use this deep kernel learning? We start by transforming the tuples, the time series data, into a fixed length vector representation. And we need to do that because the different time series data may have different lengths. And then we create in this way feature maps that will subsequently be used by the kernel to measure the similarities between these tuples. And this is accomplished through a neural network that consists of the following components. First, the recurrent neural network learns a per instance representation of the data, and the result of this step is then given by the matrix HT. Then we pass this matrix HT through a deep sets network in order to obtain a permutation invariant embedding, which we denote ZT. This is important because we want the embedding that is independent of how the individual rows are ordered in the original matrix HT. And then we take this vector ZT and XT and are concatenated and fed into a multi-layer perceptron that generates the final feature map. And this is what is used in the end to learn the similarities between data tuples and enable us to exploit the correlations across the different black box functions and use that to select the best model for the current time. Next, Fergus is going to talk about how we can make these machine learning models not only perform well through the use of automated machine learning, but also interpretable.
Thanks, Mihaela. So as Mihaela mentioned, we're now going to discuss interpretability. And this is particularly key in a high-stakes scenario for medicine and absolutely essential for doctors when using machine learning models. However, interpretability in the time series setting becomes much more challenging, as we'll see. I'm going to begin with a brief discussion of what type of interpretability we're going to be discussing in today's tutorial. So the two central paradigms of interpretability are intrinsic or post hoc interpretability. As the name suggests, intrinsic methods are inherently interpretable and provide an explanation together with the output prediction. In this tutorial, we're going to focus on post hoc interpretability methods that equip a black box model F with an explainer that provides an explanation for the output of the black box model. A key advantage of post hoc methods as opposed to intrinsic methods is that they can be applied to any black box model F. So perhaps the most common type of post hoc interpretability is feature importance or feature saliency. To illustrate this, let's take an image classifier that predicts whether an image is of a dog. And how can we explain the reason the black box predicted this image to be a dog? The idea of feature importance is to highlight the parts of the image or the input X that motivates the prediction. For instance, a model might pay attention to certain parts of the image to detect a dog, such as its nose or ears. Two common approaches for feature importance that are widely adopted in the static setting are integrated gradient and Schaar. However, Ismail et al. Showed in a recent paper that such standard feature importance methods perform poorly in the time series context. And this can be explained primarily due to the conflation of the time and feature domains. So what makes time series so special? I want to illustrate this by considering a classifier model that must decide whether it's best to wait, sell, or buy a stock by studying its price over time. As you can see here, the classifier model waits until just after a maximal price in order to sell the security, and conversely, waits until just after a minimal price before buying a security. In order to identify either a maximum or a minimum price, you need at least 3 consecutive time steps. In other words, time induces a context, and this context must be taken into account when providing an explanation of the behavior of the time series model. However, standard feature saliency methods aren't designed for the time series setting and don't naturally take this context into account. One approach for detecting salient features in the time series setting that can take this context into account is by using perturbations. And the basic idea of this approach is if you perturb a feature and it significantly affects or changes the prediction of the model, then this feature must be salient for the model. To illustrate this, let's revisit the previous example and focus on this decision to sell. So let's say we want to investigate whether the previous time step is salient for the decision to sell. So let us perturb this time step and change the price from a maximum into a minimum. You can see that once this has occurred, the model's decisions changed from sell into buy. And thus we can conclude that this input feature was salient for the model to issue its original prediction. This allows us to take the time context into account, unlike typical feature saliency methods. And we can do this by using dynamic perturbation operators. The basic idea behind such perturbations is that you can perturb each observation by using the neighboring points in time. Formally, as you can see here, the perturbed input can be expressed as a linear combination of neighboring times for some function Ct. And by doing this, you can integrate the time dependency into the perturbation operator itself. Let's consider a simple example to illustrate this. So if we consider this time series, and suppose we wish to perturb a specific time t star, what we can do to construct one of these dynamic perturbation operators is take a window around this point in time and use all of the inputs inside this window to build our perturbation. Note that there's not just one possible perturbation operator you could choose. For example, let's say we only have access to previous values of the time series. We could, instead of using a window around the time point, define our window so that we only include previous values of the time series. And this is obviously a consideration to take into account when designing your perturbation operator. So at the moment, this idea is slightly ad hoc, but hopefully the idea and motivation is pretty clear behind what we're trying to achieve here. So to formalize this, I want to introduce a recent approach from our lab called DynaMask. So we're given an input time series X and a black box model F that produces an output F of X. As we've said, we wish to know which parts of the time series are most salient for the black box model F to issue its prediction. This saliency can be represented by a mask that is the same shape as the input time series. And we can use this mask together with the perturbation operator to build a perturbed output. We can then compare this perturbed output with the original output to get an error, and we can back propagate the error to correct the mask to identify the salient features. However, we don't just want any mask. We want to enforce that the mask selects only the most relevant features and doesn't highlight more features than is strictly necessary. In order to do this, the user could select a fraction of the input to be highlighted and enforce sparsity via a regularization term that sets a large proportion of the coefficients to 0. In addition to sparsity, considering we're in the time series domain, we might want to avoid too many quick jumps or changes in the saliency over time as some kind of prior belief or preference of the user. If this is indeed the case, an additional regularization term could be added to the objective to penalize jumps in the feature saliency over time. And as you can see on the right-hand side, the effect this has would be to smooth out the saliency map to make smoother transitions in the feature importance over time. We'll just finish this section by concluding with an example of the saliency maps from DynaMask and comparing them to baselines. As you can see, compared to the true saliency shown here, the saliency of DynaMask is very similar, whereas all of these baseline saliencies that don't take the time series context into account give much worse feature saliencies. So far, we've discussed feature-based explanations, i.e., we've tried to explain the output of a black box model with respect to that specific input example. However, there is another possible way to understand black box models, and that is with example-based paradigms. And in this paradigm, what we're trying to do is contextualize the black box model's prediction with relevant training examples that could be used to indicate why it led to the prediction it did. This is a particularly powerful concept in medicine, where doctors often want to relate the current patient to patients that they've seen before. So the goal is to explain the predictions for a specific patient using a set of examples selected by the user that represent known examples. So let's start with an example X in feature space and a black box function F that maps this individual to a prediction Y. In addition, we have the unknown examples, which form a corpus of examples also in the input space, X. This raises a natural question, which is how can we decompose the example X in terms of the corpus examples in order to reconstruct the black box prediction Y? So let us begin with a naive approach for this. We can obviously express X as a weighted combination of the corpus examples and interpret the weight of each as a measure of the importance of the corpus example for the example we're trying to explain. However, the problem with this approach is the black box is typically not a linear map, and hence the weights used to make the decomposition in the input space won't be conserved if you were to perform the same decomposition in the output space. And thus we can't use the weights in input space as a measure of the importance for the black box predictions. And the real issue here is that the input space doesn't necessarily reflect how the black box represents different examples. So what can we do instead? Typical machine learning architectures will often map the input space X into a latent space before issuing a prediction. What we can do is we can interpret this latent space as a new feature space learned by the black box in order to solve this problem. And with these new features, the black box can be seen to compute the output with a simple linear map. Of course, we can take the composition of these two functions in order to recover the black box. However, when we now make a corpus decomposition in this latent space H instead of the input space, the weights are preserved between the latent space and the output space, since the map between these two spaces is linear. And hence the latent space seems to be the right space in which to perform this decomposition. Now, an obvious question is, can we perform this kind of decomposition for every possible samples? And can we do this perfectly? And the answer is not necessarily. And to see this, let's use this example shown here. With a non-negative decomposition, the corpus examples induce a corpus hull in the latent space, which contains all points in the latent space that can be perfectly expressed as a mixture of points in our corpus. However, in this example, the point we're interested in, H, is actually outside of this corpus hull. We can still construct the best possible corpus decomposition of the example H hat, but note that this decomposition isn't exact, and there is an error in our decomposition. We can call this error term the residual, and we can see later on that this quantity is actually very insightful when considering explanations of black box models. I'd like to briefly note that while we've obviously focused on which examples are included in our decomposition and how to construct this decomposition, our formulation actually also allows us to ask which features of those examples are particularly important in this decomposition by generalizing the integrated gradient approach. However, for details of this, I'm going to have to refer you to our paper just in the interest of time. So when we put this together, we get a method which we call simplex. And here are two examples of explanations provided by simplex. And so as you can see, the test example on the left-hand side is explained by a weighted combination of examples from the corpus with the most relevant features in these examples for their inclusion also highlighted. A really key point to note is that the explanation isn't tied to a specific set of examples, such as the training set. And this gives the user the freedom to choose the corpus of examples to explain the model predictions. And they can choose these examples in a way that makes the most sense for them when wanting to explain a black box model. This puts the human in the loop and allows explanations to be tailored to the user and leverage the user's existing knowledge base in order to explain black box models. Crucially, as well, through the use of the residual, it can allow humans to debug models and detect examples for which the user should perhaps be more skeptical of either the model or the explanation due to extrapolation outside of the corpus examples that the users provided. I'd just like to finish this section by exploring this point via a brief example with some time series. Let's consider training a time series model on a data set of non-oscillating autoregressive time series. And let's construct a test set consisting of some non-oscillating time series that are consistent with what the model's seen during training. But let us also corrupt this testing set with some oscillating time series. Clearly, the model hasn't been trained on such oscillating time series, and so it shouldn't be able to handle these particularly well. Now let's make corpus decompositions for each example and compute the residuals for all of these test examples. And the question we have is whether or not the oscillating time series can be detected using the corpus residual. To do this, let's sort the time series by decreasing order of the residual and inspect the time series in this order, and increase the counter shown on the y-axis each time an oscillating time series is detected instead of one of the non-oscillating time series. So here we can see that in general, the oscillating time series have a worse corpus approximation and therefore can indeed be identified by a larger residual compared to the non-oscillating time series. And interestingly, this simplex approach offers much better detection than a nearest neighbor baseline for performing this, showing that we're really understanding the latent space learned by the model much more deeply. So with this, I'm going to pass back over to Mihaela to discuss uncertainty estimation.
Thank you, Fergus. So we described so far methods to make the predictions of machine learning models more interpretable. However, are these predictions trustworthy? For that, we need to do uncertainty estimation. So what you see in here is a recurrent neural network, but we can take other type of machine learning models for time series forecasting. And what we would like to understand is how confident the predictions are, how create confidence intervals associated with the predictions of such machine learning models, whether deep learning models or other machine learning models. Let's explore some of the existing solutions for that. Some are Bayesian recurrent neural networks, where we are putting a prior over the recurrent neural network parameters, and the uncertainty is in the form of credible intervals. Other methods, such as quantile recurrent neural networks, are explicitly training a multi-output recurrent neural network to predict the confidence intervals. And probabilistic recurrent neural networks, whether it's attentive state space models, which we have described before, or other machine learning models, such as, for instance, deep state space models, are combining recurrent neural networks with variants of state space models and creating this way the confidence intervals associated with them. But are these solutions for uncertainty quantification enough in healthcare? The answer is no. Why is that? First, we need to provide trustworthiness in the form of post hoc uncertainty estimation. Why do we need that? Because we want to have methods that look at uncertainty quantification that do not affect the model accuracy. So they should not interfere with the model training. Also, we need generality and versatility. We do not require changes to the model architecture, such as some of these methods require. And also, we want to apply them to a wide range of sequence predictive settings. For instance, not only RNNs, but also LSTMs and GRUs. Last but not least, possibly the most important requirement in healthcare is that we do not want credible intervals, like the ones that are provided by all the other methods described previously. Instead, what we need is formal frequentist procedures that provide us frequentist coverage guarantees. So one solution was developed by us a few years back in the form of frequentist uncertainty estimation through blockwise influence functions. So the uncertainty intervals are measuring the variability in this resample, for instance, RNN or other machine learning methods outputs, as shown in here. But how are we going to be able to do that? We are going to be able to do that by resampling. So we are going to create these RNN outputs by resampled by perturbing the model parameters through iterative deletions of blocks of data, as shown in the left, and retraining the model on the remaining data. In this way, we are creating this diverse resample RNN outputs that can be used to estimate the uncertainty intervals. Let us now go back one step and talk not only about how we can make machine learning more robust and more interpretable, but also how to deal with the practical problem of missing data. A lot of the work that we have described so far assumes that we have data that is acquired at regular time intervals. but this is not the case in medicine. One solution to deal with that is to impute the missing data, thereby creating regularly sampled data. One of the possible methods is to use multi-directional recurrent neural networks that enable us to, on one hand, interpolate the missing data within a time stream and across the time streams impute. So because we have over time data that may be missed across the different streams. So at one particular data point, we may take a particular measurement, but not at another, and vice versa. We need to exploit over time and across streams, over time the temporal correlations, and at a particular moment in time, the cross-feature correlations. So these correlations across time and across features need to be explored and learned simultaneously. And this is what this multi-directional recurrent neural network is doing. What you see in here is the sequential operation of this multi-directional RNN across streams and within streams. And what you see is that the timing of inputs into the hidden layer is both lagged in the forward direction and advanced in the backwards direction. So unlike, for instance, bidirectional RNN, which are not causal, so they require information from the future to impute the current information, and hence they cannot be used in practice because we do not know the future. In the multi-directional RNN, by creating this architecture where we just use the lagged information, we can impute across the different observations without violating causality. And what you see here is that not only we can explore these correlations and learn them for imputation, but also if you want to do multiple imputations, so in other words, we want uncertainty estimation associated with the imputed values, we can rely on a variety of technologies, inclusively Monte Carlo dropout. Now, this is one way to deal with the irregularity of missing data. But the question is, can we do better? Because data in medicine is not missing at random. The fact that certain clinicians have decided to measure information at a particular moment or not is based on clinical judgment, contains information. And hence we can learn from this informative sampling on data. So because the data is shaped by these clinical judgments, it enables us to build probabilistic models for learning not only from the value of the observed data, but also the timing of the observed data. So we are going to model the patient trajectory as a mark point process, which is modulated by their inherent health state. And the nature of such informative sampling is problem dependent. For instance, if we model in the mimic data set cancer patients that are in the hospital, we have evidence that the sampling rate increases when the patient is in a bad healthcare state. So in other words, if the patient is getting worse and worse, they are going to be monitored more and more. Conversely, if the patient is doing well, they are going to be monitored less and less. So this is information that is pertinent and that we need to capture when learning from data. So how can we do that? The clinicians observe the patient's observations according to what we call a Hawkes process. And this is a doubly stochastic point process that is capable to capture the impact of the patient's health state on the clinician's sampling behavior. And we are modeling this with a self-exciting triggering kernel that is able to capture the dependence between the observation events. It is important to note here that Hawkes processes are a superset of uninformative Poisson processes. So we can do better inference by using not only the observations, but the timing of the observations. And this is shown in here. In the early part of this tutorial, we discussed how we can use the value of the observations, but not the timing of the observations, to infer, for instance, through hidden Markov models or attentive state space models, the underlying hidden state of the patient. Here, what I'm showing is how we can learn on the basis of the intensity of observation, rather the value of the observation, the underlying state of the patient. And what you see here is that because we model these observations times using the Hawkes point process, we can observe that if the patient has a lot of samples being measured, so the intensity of the acquisition function is high, the patient is in a worse state than when the acquisition function shows that relatively few observations are set. So we can in this way learn additional information about the underlying state of the patient from the clinician judgment of acquiring information. Let me now go to the final part of this tutorial and say, well, we can do all this, but only if we have high quality healthcare data to learn from. And the reality is that healthcare data is not easily accessible. And this is the result of perfectly valid concerns regarding privacy. Hence, such privacy regulations are well understood, but they impede the research that we would like to do in machine learning. So what can we do? One solution is to de-identify or anonymize data. This is real data with all personalized identifiers removed. But we can also use another approach. We can generate synthetic data, which is data created from scratch that cannot be synced back to any individual. And for that, we can use machine learning model itself. And we can use, for instance, deep generative models to generate such synthetic data on the basis of real data. As a matter of fact, in ICML 2021, we gave a tutorial on synthetic data generation, and we described how synthetic data can be used for machine learning modeling and how this is itself a challenging machine learning problem. The objective in the time series setting, which forms the part of the tutorial today, is to generate synthetic time series data that preserves the temporal dynamics. So we want to do synthetic time series data generation. The challenge, though, to generate high-quality synthetic data for time series is that we need to capture the distributions of features within each time point, as well as complex dynamics of those variables across time points. One particular solution that we have proposed a few years back is to use time series GANs. And what you see in here is how this time series GAN has been trained using a variety of losses that capture not only the joint distributions, but also the conditional distributions as well. And the time GAN hence represents the intersection of multiple strands of research in machine learning. On one hand, GAN-based methods for sequence generation, autoregressive models for sequence prediction, and time series representation learning. All of this need to be put together to generate high-quality time series synthetic data. And an advantage of TimeGAN is that it handles mixed data setting containing both static and time series data that can be generated at the same time. And this is important for healthcare, where we need to deal with such a mixed data setting. But GAN-based models are having their own limitations. They are difficult to train, especially for time series data, and are hard to evaluate quantitatively due to the absence of an explicitly computable likelihood function. Also, they are vulnerable to training data memorization. And this is a problem that can be further exacerbated in this time setting. So another solution to deal with this is to build generative time series models using Fourier flows, which are enabling us to generate sampling time series data and are providing us explicit likelihood models, which are easy to optimize and easy to evaluate. More about this in our ICML 2021 tutorial on synthetic data generation. To conclude this talk, I would like to say that today we describe to you different ways in which we can look at the challenging problems set by healthcare. And we describe to you these various approaches, whether it's dynamic forecasting, time to event analysis, survival analysis, dynamic treatment effect estimation, early diagnosis, temporal clustering, or personalized screening and monitoring over time. But the reality is that these problems are interconnected. So a new frontier is how we can build an integrated ecosystem of tools to empower clinicians and patients. And as these different methods interact, new frontiers of machine learning are going to arise. So to catalyze a true revolution in healthcare, we need to bring these methods together, and we need to think how they can make an impact on the patient, on the healthcare professionals, how they can enable system pathways and processes in healthcare, and more generally, population health and public health policies. If you are interested to talk to Fergus and me beyond this particular tutorial, as well as the other researchers in our lab, we would like to one more time invite you to join our Inspiration Exchange engagement sessions that are happening every month. Please join us.